Students, this is chemistry class number 84. So we are continuing the ordination compounds chapter. Ultimately, let us study the stability of ordination compounds. How actually they are stable, to what extent is it. So this stability of ordination complexes or ordination compounds in solutions we are going to take. In solutions refers to the degree of association, not degree of dissociation. Degree of association, that means stability of coordination complexes in solutions refers to the degree of association of two species involved in the equilibrium state. So therefore, if you consider, because you see here there is the complex entity in coordination compound is unstable, hence it decomposes to a very little extent. It is unstable, therefore it decomposes to a small extent. Since it is stable, okay, it decomposes to a small extent. So therefore, stability of coordination complexes in solution refers to the degree of association of two entities or two species involved in the equilibrium state we are going to take for the association. So therefore, if after the equilibrium state, if we calculate the equilibrium constant, that equilibrium constant K for the formation of this complex entity itself is not the stability constant. So that means stability constant or stability of coordination complexes in the solutions refers to the degree of association between the two species which involved in the equilibrium constant. It's an equilibrium state. So due to the equilibrium state, we can calculate that is a equilibrium constant. The equilibrium constant for the formation of the complex entity, okay, refers to stability constant. That is called stability constant of the coordination complex. Stability of coordination complex is defined as it is the constant which is obtained during the formation of the complex entity. So let me take an example for this stability constant for the formation of some complex entities. So let me take the first example. That is a stability constant. You see, stability constant for the formation of Cu NH3 4 times 2 plus ion. That is bromonium ion. So it is obtained by the combination of Cu2 plus with that is 4 NH3 molecules. Ligands, 4 NH3 molecules as ligands. Then you will get it. That is Cu NH3 4 times 2 plus ion. So that is Cu2 plus 4 NH3 into Cu NH3 4 times 2 plus ion. So after the equilibrium state is the formation of bromonium ion, let us calculate this K. That means K can be calculated as K is equal to, that is the concentration of Cu NH3 4 times, or you can write here K is equal to Cu NH3 4 times 2 plus divided by concentration of Cu2 plus, or you can write here, okay, that is K is equal to Cu NH3 4 times 2 plus divided by concentration of Cu2 plus into concentration of NH3 to the power of 4 using 4. So and this is called the equilibrium constant. You see, this equilibrium constant for the formation of this complex entity is called as the stability constant. That is, what is the value of this stability constant for the formation of bromonium ion? It is found to be 4.5 into 10 power 11, that is K. Value is 4.5 to 10 power. Therefore, they have got high magnitude. So let me calculate the stability constant for the formation of ferrocyanide ions. That is for ferrocyanide ion. So that is therefore Fe Cl6 in that you see FeCl6 4 minus. So then for this you see Fe2 plus 6Cl minus 6. You will be getting, that is FeCl6 4 minus ion. And if you calculate it, there is K, then K is equal to, that is concentration of FeCl6 that is 4 minus divided by concentration of P2 plus P2 concentration of that is Cl minus to the power of 6 to the power of 6. That is nothing but 6Cl minus means Cl minus to the power of 6. So this value of this equilibrium constant is told to be, it is very very high, that will be equal to 1 into 10 power 6, 1 into 10 power 6. So for ferricyanide ion, let us say take ferricyanide ion. So that is K3 efficiency, K3 efficiency 6, efficiency 3 minus. So for that you can calculate that is Fe3 plus 6Cl minus. You will be getting that is FeCl6, that is 3 minus. So for this you can calculate that is K is equal to that is FeCl6, that is 3 minus divided by Fe3 plus into Cl minus to the power of 6, and this value is found to be that is very very high, that is 1 into 10 power 31. 1 into 10 power 31. That is K value. K value is nothing but 1 into 10 power 31. It is 1 into 10 power 6. It is 4.5 to 10 power 11. That means you see that is your stability constant values are very very high for the formation of these complex entities. So generally, greater the stability constant value, that means higher the value of stability constant, that is K, greater is the stability constant for the complex entities. So there is a higher value of K indicates that you see there is a greater stability constant for the complex entity itself. So after that you see generally stability will increases by addition of ligands. If you add ligands, the stability will be increases. So by adding the ligands, you see, so here it is only 4, it is 6. Like that you see, if you increase the number of ligands, the stability also increases. That means stability will be increases by the addition of ligands. How actually we can calculate that also you see. So totally we come to the conclusion that what is stability constant for the coordination complex? That is the equilibrium constant for the formation of complex entity itself is called the stability constant for the coordination complexes. Generally higher the stability constant, so greater is the stability constant for the complex entity. Okay. So after that you see, let me add one by one, that is the if you add the number of ligands, addition of ligands will increase the stability of the that is complexity. So that is, if I take that is M plus L. So this is metal. Adding this ligand is M plus L, we will be getting Mn is Mn. So for that we can write K1 is equal to that is concentration of Mn divided by concentration of M into concentration of L. So therefore that is this is K1 we see, this is K1. So if you take one more, that is Ml plus L. So then we will be getting Ml2. That is K2 we can calculate, that is Ml2 concentration of Ml2 divided by concentration of Ml into concentration of water, L. So again Ml2 plus L, we will be getting Ml3 is Ml3. We can calculate the equilibrium constant K3L, that is K3 is equal to Ml3 divided by water, Ml2 into L. So this is how we can add the ligands one by one. So that stability of the complex entity also increases like that. You see, that is Ml3 plus L. You will be getting Ml4. You see, M plus L, Ml. Ml plus L, Ml2. Ml2 plus L, Ml3. Ml2 plus L, Ml4. That means addition of ligands increases the stability of the complex entity. That is F4 is equal to Ml4 divided by concentration of Ml3 into concentration of water, L. That is how we can add the ligands. So that means you see for this where this K1 K2 is K1 K2 K3 K4 etc. So these are the stepwise stability constants. Stepwise stability constants. Stepwise stability constants. They are called as, so 1, 2, 3, 4. Therefore, stepwise stability constants. So if you calculate the overall stability constant, so that is overall stability constant we can calculate. So that is nothing but B4 you see beta 4 is equal to K1 into K2 into K3 into K4 etc. So in general we can write as that is Bn beta n is equal to K1 into K3 K2 into K3 etc. Kn. So that is how we can write the in general you can write the that is stability constant. Okay. That is these are K1 K2 K3 stepwise constants, overall constants, stability constants beta 4. Generally we can call it as beta n. Okay. That is K1 K2 K3 and what Kn. That is how we can calculate the stability constant for coordination complexes or complex entities. So if we take one more an example for this use for this. So I will take that there is formation of that is your cryptoammonium ion itself for the same thing. Let me write the stepwise stability constants for each level step you see. So that is formation of that is cryptoammonium ion. For this that is let me take that is Cu2 plus NH3 Cu2 plus NH3 M plus L like that. You will get Cu NH3 CNH3 2 plus. Okay. So if we take that is K1 is equal to concentration of Cu NH3 2 plus divided by Cu2 plus into concentration of NH3. Okay. So this is first. Next second one is Cu NH3 that is 2 plus again one more ligand is NH3. So then we will get Cu NH3 twice 2 plus and K2 becomes that will be equal to that is Cu NH3 twice 2 plus divided by that is concentration of Cu NH3 whole 2 plus into concentration of water NH3. So this is how we can go on writing the stability constant equations. That is Cu again Cu NH3 twice 2 plus again one more ligand NH3 and you will be getting Cu NH3 twice 2 plus that is divided by concentration of Cu NH3 twice 2 plus into concentration of water NH3. You can write like this NH3. Therefore K3 is equal to concentration of Cu NH3 that is not we write only this much here. That is K3 is equal to Cu NH3 3 times 2 plus divided by concentration of Cu NH3 twice whole 2 plus into concentration of water NH3 into concentration of NH3. So that is K3. If you take K4, that is the fourth step Cu NH3 thrice 2 plus again one more ligand NH3. Finally, we will be getting the product that is Cu NH3 4 times 2 plus ion. That is called the cryptoammonium ions. So that is the now K4 is equal to Cu NH3 4 times 2 plus divided by concentration of Cu NH3 3 times 2 plus whole 2 plus into concentration of water. So this is how we can write the equations, many number of equations for this you see. So generally finally we can write the overall equations for the overall that is constants for this also. That is where K1, K2, K3, K4 are called that is stepwise stability constants and overall constants beta 4 is equal to that is K1, K2, K3, K4 etc. beta n. For the formation of ammonia, so we can write that is values important values for K1 equals K2 equals K3 equals K4 equals. That is, you can write the values for this stepwise stability constants. You see. So that is for K1 it is found to be 4.0. That is that is K1 log K1 is equal to, that is log K1, you can write log K1, log K2, log K3, log K4 is it. That is first stepwise constant is 4.0. Next one is 3.2. That is K2 is found to be 3.2 and then 2.7. Third one is 2.7. That is last one is 2.0. If I add this, it is found to be 9. This is 2, 4, 4 plus 3, 7, 7 plus 4 is 11.9. Overall stability constant, the total log before log beta 4 is found to be 11.9. 11.5. So this is regarding the stability of coordination complexes. What is the instability constant? If you want to calculate instability constant, so instability constant is nothing but dissociation constant. Stability constant, we are the formation constant we are going to take this. For the stability of coordination complexes or stability constants, we are taking the formation of complex entities, formation constant, let us say, or equilibrium constant. But instability constant, that is for instabilities of coordination compounds or instability constants, you see, it is nothing but it is the reciprocal of formation constant. What is that? What is meant by instability constant? Instability of coordination complexes is defined as it is the reciprocal of formation constant. Formation constant. So what is formation constant? It is nothing but equilibrium constant. What is formation constant? Equilibrium constant. Therefore, instability constant is equal to instability constant is equal to the 1 by that is formation constant. Equilibrium constant. Yes. Instability constant is equal to 1 by that is formation constant. So reciprocal of formation constant is called the instability constant. So that is K1, K2, K3 are called the formation constants actually. So therefore those formation constants are also called the equilibrium constants. So therefore you see, if you want to calculate the instability constant, you just take the reciprocal of the formation constant, that is nothing but your instability constant or instability of coordination complex. That means you see, you have to calculate the formation constants or stability constants reciprocally, you will be getting instability constant. That's it. So that is how we can calculate the stability constant and instability constants for the coordination complexes. So that completes your coordination complexes, I suppose.